Motions in the universe are quite different from motions we are used to. Things around us move through space. But in the universe, in cosmology, it is space itself that changes. More space is created as time passes. How can the structure of space determine how things move? You can understand that from the following. Imagine I have a bit of space here, a two-dimensional bit of space with two parallel lines on it. I am going to change the structure of that space. I will remove a bit of it. I make a cut. And I change it. So here the lines are parallel, and now they are curved. So the more space I remove, the more curved it becomes, and the more curved these orbits become. Curved space results in curved orbits. Since 1916, when Einstein published the theory of general relativity, we know how to calculate the changes in space and time. When applied to the universe as a whole, you obtain a so-called cosmological model. And it turns out that in our universe, more and more space is created as time passes. What do we see of all that? When you look into space, you look back into time, because nothing can go faster than light. So when we look at the moon, we see it as it was 1.3 seconds ago. When we look at the sun, we see it as it was 8.3 minutes ago. When we look at the Andromeda galaxy, 2 million years, etc., etc. So if you stand somewhere, wherever that is, and you look into space, you see the entire history of the universe along that line. And what do we see? As time passes, more space is being created. That means earlier on there was less space, but for the same amount of matter and energy. The universe was more compact, thus hotter. There was more energy per cubic meter. When you go back far enough into the history of the universe, there is a point where it was glowing with heat. We should be able to see that glow from the Big Bang, the very beginning of the universe. But you know that at night it is dark. You don't see any glow at all. How is that? That again is due to the expansion of the universe. More space is created. The waves of light that were emitted from the glowing universe are stretched out due to this expansion, whilst travelling towards us. Initially, those waves were emitted in the visible light, very much like our sun emits visible light. We will be able to see that light with our eyes, but by the time they arrive at Earth today, they have been stretched out to such an extent due to the expansion of the universe that they have become microwaves. Our eyes are not sensitive to microwave radiation, and thus the night looks totally dark to us. But with experiments such as Planck, we can detect the microwave radiation. We can see the glow of the Big Bang. This radiation was predicted in 1948 by George Gamow and his collaborators. It was discovered by chance in 1960 and it has become one of the cornerstones of cosmological research. By studying radiation from the very beginning, we obtain a photo of the universe at an initial stage. From that, we can try to determine how the universe must have been created. In fact, what we measure is the temperature of the early universe. That temperature is not the same everywhere. There are small irregularities, small ripples, about 1 out of 100,000, so very smooth, but they are still irregularities. These ripples are caused by vibrations of the matter in the early universe, much like sound waves, comparable to the vibrations that my voice produces in this air, and that your ears can hear. Similar sound vibrations were present in the very early universe. But how can you, from vibrations, know how something is built, even if you cannot see it? You can understand that from the following. I have here a glass, and when I tinkle on it, I hear a certain tone, because I make the glass vibrate. Imagine, I now fill this glass with something. I fill it with some water, and tinkle on it again. The tone is now different, and when I fill it completely, the tone is again different. Very low. The first tone was high. This tone is low. So even if I cannot see what is in the glass, I know from that sound that there is something in it. For example, we know from the vibrations of the Earth, from earthquakes, what its interior looks like. From vibrations on the surface of the Sun, we know what its interior looks like, even though we cannot see it. And in a similar way, we can know what happened in the very early stages of the universe by looking at the vibrations of the cosmic microwave background radiation. Radiation has a certain temperature, just like the temperature of our Sun corresponds to the radiation it emits. You can determine that temperature and see the fluctuations of it over the sky. These fluctuations are of the order of 1 out of 100,000, and that is very small indeed. But you can detect them if you observe accurately enough. They exist because at certain places in the universe, there is slightly more matter, and in other places there is slightly less. Due to this matter, space is locally being curved, just a little. We have seen it before. When you take some space, you place matter on it, it curves, and the orbits change. The same applies to light. So not just orbits of matter, but also those of light, change due to the curvature of space. Those changes become apparent as a change in temperature. Thus, you can trace any tiny changes in mass density in the universe by studying the corresponding changes in temperature. Why is Planck needed? We have known about the cosmic background radiation since 1960. And previous satellites like, for example, COBE and WMAP have already mapped the sky. When you think carefully, you understand that the more detail you know about the vibrations, the more details you can obtain about the very early universe. When you look at the microwave background map made by the COBE satellite, you can see some spots here and there. That is nice. The improved map made by the WMAP satellite resolves these larger spots in small speckles. From this, we can derive the state of the early universe much more accurately. The observations that Planck will do will be even more accurate, and thus we will be able to learn even more about the extremely early universe, not just about today's 13.7 billion years, not just about the 370,000 years after the Big Bang when the microwave radiation was emitted, but almost all that precedes this. Thus we almost reach one of the goals of astronomy, to know the entire history of our universe. That is why Planck is so important.